Good afternoon. This is 6004. My name is Arvind. I'll be sharing lectures with Silvina Hanano, and Jason Miller is also may lecture sometimes. We have an excellent team of teaching assistants, and you should get to know them because they are the most helpful resource in the course. They're all here. Why don't you all stand up and show your hands. Very good. Okay, so today's lecture is to set up what this course is about, what you'll be learning, and so on. So, you know, it's really amazing how much change has happened in computers. So this is the picture of the very first one, you know, from 1943, ENIAC. The things that stand out about it is that it weighed 30 tons. And when it was turned on, the lights in Philadelphia were dimmed, right? Consumed so much power. And it executed amazingly 1,000 operations per second. It was amazingly fast at that time if you compare it to what people were doing by hand using calculators and so on. And now if you look at computing devices today, your laptop weighs a kg or something like that, and it consumes less than 10 watts, and it can do 10 billion operations per second. And this is all possible because of changes in technology, how technology has progressed, and how much we have learned about computers. And that's really the main aspect of this course. This is the main goal of this course, to make you understand how computers function, how computers actually function internally. And the best way to learn that is actually by building them. And you'll be building quite a few of them in this class. And as you know, computers are everywhere. I mean, it's hard to imagine a device now. I was so surprised when my son presented me this Sonos speaker, right? And I discovered that even in an audio speaker, now you have to log in to this speaker. Without that, it won't recognize your voice or something. You know, this sounds so bizarre that a passive device like a speaker is no longer passive, and it has so much computing going on inside it. But by the time you look at smartphones or smart cars and everything, I mean, there's just so much computing everywhere. And what is amazing is this general purpose aspect of computing, right? A processor may be very small or maybe very big, but they share a lot, right? The principles are the same of how we approach them. So the focus in this class is the design of general purpose general purpose processors. And you may say, I'm not into hardware design, so why are you bugging me with all this? Of course, it's good to know something about how computers work. It's good for your soul, probably, right? But really, there are many reasons why you should do this. Most important reason is they are really a crucial building block in just about any hardware you see. So understanding how processors work will dramatically deepen your understanding of hardware and how things function, right? So that's one reason why it's such a universal device, that the same device that is being used in your Fitbit is also being used in supercomputers. It's pretty amazing. The second thing is, believe it or not, microprocessors are some of the most complex things we know that are designed by human beings. I mean, it's a very, very complex device. So we focus on this because we learn lots of general principles, and many of these principles we can pick when we are designing a special purpose hardware. So it's almost never the case that somebody shows me a special purpose computer, it uses some trick that I have not seen already in general purpose computing. So general purpose computing also incorporates many, many hardware techniques which are broadly useful, even when you're not building a general purpose hardware. So there is a lot to learn about general purpose computers and how they function and how they should be put together. What does it mean to have a balanced system? And the proof is in the pudding. So by the end of the class, you would have actually designed many computers, not just one, many ones, which are different internally, but they will all run the same software. And that's the beauty of it, right? So we can have some software that runs, and tomorrow you can say, oh, actually I want a device which will run it much, much faster. Or I want to run this program on some other device which consumes dramatically less power. So that's why there is so much variety in processor design, because depending upon what we are focusing on, the design will change quite a lot, and you'll get some feel for it. I want to emphasize the word general purpose as opposed to special purpose. Well, you already know programming, right? So you at least are familiar with Python or some other programming language like that. Now, one simplistic view of the course will be, we are going to build a Python machine. Far from it, actually. That's not what we are going to be doing. Because we don't want to build a separate machine for Python and for Java and for this and for that, right? It's universal. We want to build some piece of hardware on which we can execute any programming language that we want, any high-level language that we want. In fact, when we program in high-level languages, we don't pay attention to what is at the low level of hardware in the system. And that is the beauty of high-level languages, right? We can abstract away from lots of details which are underneath the machine. So obviously, I would like the same piece of hardware, and tomorrow if you invent a better language, I would like to learn that language, run that language also on the same piece of hardware. The second thing is more subtle, and this will take some time to appreciate. It does not make sense to do everything in hardware, right? Hardware is very, very good at doing some things. It can do it super fast. But if you try to do some other things in hardware, it's belabored. It doesn't make sense. You could have easily done some other way. You could have done it in software or do some other game with it. So we have to develop a feel for what is easy to do in hardware. And then how do we connect this high-level language, Python, Java, C, that you know, with this other piece of device we had, which we are calling general purpose universal device. So this is the picture I would like you to keep in mind. So at the high level, you have all these languages, a plethora of languages. In the middle, it narrows down. We'll focus on a specific assembly language. There is not so much variety at that level, right? And then underneath you have hardware, you have microprocessors. So the way to think about this is, this assembly language, which you can think of it as a low-level programming language, is the real interface between high-level languages and hardware on which things will execute. And this interface is extraordinarily important. The first unit of this class is all about learning this interface. How do we interact with lower-level devices? And this interface is designed extremely carefully. A lot of research has gone into it. There is tons of experience built over the last 70, 80 years of how this instruction set should look like for this low-level language. The beauty of it is, this is what hardware executes directly, right? So we want to bias it. We want to choose something, an interface, which is suitable for building hardware, so that we can say, aha, this is what I'm implementing. But this interface also has to have this other property. It has to be also suitable as a target for many high-level languages, right? And that's where a different game comes into play, which is like software translation. We take this high-level program and we translate it into this lower-level language. This is purely a software problem. You write an algorithm of how to take this notation and transform it into that notation, right? So you will learn that. You will learn, that's not the focus of this class, but at least you'll get a glimpse, that what is the connection between high-level language constructs and low-level assembly language that we need in this class, because that's what we will be implementing in hardware. And if this is done right, then it provides complete isolation When you program in high-level language, you'll never be thinking of low-level hardware, right? And when you're designing the low-level hardware, you do not think in terms of high-level languages, except in terms of program behavior. Exactly what are you trying to do in the high-level language, because that can bias the decisions I take at low level. But there is no one-to-one direct correspondence with the high-level ideas and the low-level hardware that we will be building in this class. So there are some facts, and I call them facts because I can't derive them. That's how it is. And one of them is that all modern electronic computers are digital. That is, they compute with ones and zeros. They certainly don't work with, decimal numbers. They work with, binary numbers, ones and zeros. There are very, very good hardware reasons why we want to deal with just ones and zeros. It's much more resilient. We know how to build it very well. And it turns out mathematically also it's much more efficient to deal with ones and zeros than to deal with some other encoding of numbers. Now, all the information, numerical information, alphanumeric information, everything ultimately is converted in ones and zeros. You may be following many conventions to do that, but inside computers, everything is going to be represented as ones and zeros. And what you will discover is that we can perform many operations on these ones and zeros, like addition or compare two numbers, or to do logical operations on them, and or operations, negation of these bits, extremely efficiently in hardware. Very, very efficiently in hardware. So it may be tedious for you to write down a big binary number, but at the hardware level it's super efficient to do it at the binary level than to do it at decimal level or some other representation. Now, this is the unwritten rule. Anything we talk about in this class is extremely technology dependent. Even though we don't talk about technology, we will not be discussing CMOS. We will not be discussing the actual circuits at the low level here. But the way this technology has evolved is completely embodied in the design principles that you'll be discussing all the time. So we are abstracting away from low-level technology. But the thing to remember is, suppose tomorrow, there was a revolution in technology and somebody says, the silicon stuff is old and it has reached some maturity and it's not going anywhere, which is not true yet, but it's slowing down, right? And people may come up with completely new technologies like, computing based on DNAs. People are already using DNAs for storage, right? Encoding in DNAs and trying to manufacture those things artificially. If such a radical change happened in technology, the structure of computers will look very different. It's likely to look very, very different. So whenever we make an argument, oh, it's like this, or this is more efficient, there is always this underlying assumption that we are dealing with silicon technology, and these are the things experience has shown, it's super efficient to do in the technologies in which we build machines. This wasn't always the case. I mean, we have started believing in electronic computers only since about 1940. Before that, people were talking about electromechanical computers, mixing electronics and some mechanical operations, like your mechanical calculator of the old days, if you have seen one, right? And if you go back to 19th century, of the time of Charles Babbage, it was 100% mechanical. So yes, it's possible to compute even without electronics. We can build very sophisticated calculators, but the modern progress in computers have all to do with electronics, have all to do with silicon. How we can build these things cheaply, we can build very complex things. They're extremely reliable, they're extremely resilient, they don't break down so easily, etc. So just remember that we are talking about silicon-based computers, even though I will not be discussing silicon per se all the time in this class. Now let me talk about the essential aspects of this middle thing I was showing, which I'm calling assembly language. Sometimes I'll call it machine language. The distinction will become clear, but not important for this lecture, right? It's very, very low level language, which is close to hardware, pardon me. Okay, so very essential part of this is a register file, a bunch of registers which can hold numbers. Typically you're talking of very small numbers, maybe 32 registers. Each one of them is 32 bits wide. Okay, so that's pretty typical, of this. And what happens is this is connected to a device called ALU, or Arithmetic Logic Unit. This is the device that knows how to perform binary operations. So if you give it two numbers, it knows how to add them. You can do logical operations, you can do comparisons, relational operators on this. So you give it two numbers, it produces a number. So very simple view of how computing devices work is we are always taking numbers out of this register file, right? And we compute something, and when the result is available, we store it back into the register file. This is a very, very typical operation. Read two things from the register file, do some operation on it, simple operation on binary arithmetic, and put it back into the register file over this. So this is a very, very important aspect of it. And in some sense, you're familiar with this, right? I mean, this is how you think of your calculator. Your calculator has maybe one register, or sometimes it has two registers in it, and you can type the number and you can see what is displayed. And then you type another number and you say add, and the display changes. So you have modified the register that was there. In fact, this is how it all began. Earliest computers had only one or two registers in them. But people said, it can be much more profitable if we have a few more. So now we are up to 16. Sometimes we may have more, but we are still talking of a very, very small number of registers. And that's where this computing device is connected, right? This ALU. Now this ALU in modern systems is so tiny that you will have to actually fish for it, right? Even though a lot of electronics goes into it and we will be spending a lot of time designing it. But the first picture I showed you, that ENIAC that weighed 30 tons, in ALU, if you imagine it wasn't a 32-bit ALU, it was I think 18-bit ALU, each bit was bigger than me. Can you imagine that? Right? You have 18-bit register, right? And the register would go from here up to here, right? I heard a talk on the history of computing, and this person said very proudly, says, man, those were the days when we stood inside the bit to fix it, right? I mean, this was the size of things. And now it's microscopic. I mean, it's so tiny that you'll be hard-pressed to find it. The other aspect of computers, which is very important, is they also have a lot of memory, right? They have lots of storage available, which can be... So you can think of this as when you do calculations on a calculator, sometimes you'll be taking down notes, right? Or if you're adding a table of numbers, somebody has already given you the table of numbers printed, somewhere, and you're reading that and putting that in, reading it and putting it in. So just imagine all those numbers are also, stored in some storage. We'll just call it main memory in this. Thing to take away is register files are small, main memory is very large as compared to it. In the beginning, we can just assume main memory is infinite for our purposes. It's never infinite, but it's dramatically larger than the amount of storage you have in the register file. Now, this memory holds, of course, the data. That's understandable. What is remarkable is it also holds the instructions, the program, which we use for computing. This was a huge advancement in computing. I mean, this happened in late 40s, when people figured out, oh, program is no different from numbers. I can store program also as ones and zeros and put it in the same memory. And this has huge consequences, when we can store the program also. But for today's lecture purposes, just imagine that you have this humongous storage in which you can store all your data, all the tables with which you are trying to compute, as well as the program that is needed to compute something. Program, you can think of it as a script, for carrying out instructions. When you do it on your calculator, you carry that program in your head. If the steps were very intricate, you may write down on a piece of paper, do this, do this, do this, etc. Now, another very important aspect of computers is we never compute directly on memory storage, memory locations. Whenever we want to compute, we have to move the data from the main memory into register file. And when we are done with it, then we move the data back from the register file into memory. Essentially, this is the structure of a microprocessor. So inside it, you will have a register file, you will have a lot of storage, right, which can hold lots of data and program. And register file is what is connected to an ALU, a compute engine which knows how to add and multiply and divide and God knows what, from simple to complex operations, but generally very simple operations. And then there are ways of moving data between register file and the main memory. Now, the programming we do directly reflects the structure, so much so that I can't separate the two, right? So I have an abstract view of the machine, which is this. And when you write your program, you will have this kind of a structure in your mind. Now, this is already very different from high-level languages. In high-level languages, you have a variable. You don't draw this distinction that this variable is sitting in the register or is sitting in the memory. You just think of some storage element. There is some X, in which this variable is sitting, and I manipulate that variable. In low-level programming, in this assembly language programming, we draw a huge distinction, because if you want to operate, if you want to add two numbers, I must bring them into the register file and then apply ALU to it. And I will explicitly move information from the register file back into the memory and from the memory into the register file. Okay, so let's just summarize what we have seen so far. So each register is of fixed size, right? Typically 32 bits you're talking about. Sometimes we'll talk about 64-bit registers. But that's the kind of thing you're talking about. And they're all the same size. Number of registers is also small, say 32. Now, ALU performs operations on registers file, typically operations of this sort, that you have xi gets some op applied to xj and xk. These are the names of the registers in your register file, right? And what kind of operations we are talking about? Say plus or and or less than, etc. So there might be of the order of 24 primitive operations like that are defined, which you will be learning precisely in the next lecture. So far so good? All right. And then we have memory, which instead of talking in terms of, we have 32 words, we talk in gigabytes. We have lots of memory, many, many words. And the words are typically, 4 bytes, 8-bit bytes, that's how it's organized. And data can be moved back and forth. So the instructions for moving things back and forth are called load and store. So you have load, so you're taking some address, taking something from the memory, moving into register X. That's a load instruction. And store is the complement of it. You have some data in some register and you're saying move it into the memory, into this address that I'm giving you. So this is the essence of it, that we will perform operations on registers, simple operations on registers, and we can move data back and forth. There's only one thing missing, so let's understand that. And for that, we have to understand the notion of a program. So typically, when you write an algorithm, if you were to write a procedure, you will write it linearly. You'll say do this, and then do this, and then do this. Straight line. But suppose you are doing something 1,000,000 times, it can get a bit tedious if your program also was 1,000,000 lines long. So we need some other ways of doing it, and sometimes we want to skip steps because I want to do this only if some condition is true. So these are called control transfer instructions. So now to complete the picture, we have 4 types of instructions. We have ALU type instructions, which take 2 things out of the register file, perform some operations, store the result back into the register file. We have load instruction, which moves the data from the memory into register file. We have store instruction, which takes the data from the register file and puts it into a specified location in the memory. And then we have control transfer operations. So a typical control transfer operations may be that you compare 2 numbers. You compare 2 registers, xi and xj, 2 registers again. And it says, oh, if it's greater than that, if it's less than that, then go to label I. What is label I? Label L. So label, if you imagine your program is stored linearly, 1, 2, 3, 4, 5, 6. So here I execute this instruction. If it is xi is greater than xj, jump to L. So you would have assigned a name to every location in the program, and you say, please go there. This is altering the control. This is, instead of executing things sequentially, suddenly under some circumstances you are saying, oh, no, don't go on like this, but instead jump here or jump there in this. Okay, so what I'm going to do is, I haven't given you enough detail, but nevertheless we're going to try to write a program, right? And I'm going to rely on your intuition, and then we'll fill in these details again tomorrow and in the next lecture and so on. So let's try to write a program which sum all the elements of an array, right? So I have an array of n elements, A0, A1, A2, and I want to sum them all up. Assumption here is we know how to add 2 numbers, right? I mean, that's what my ALU operation is. I know how to add it. The next assumption is going to be that this array is probably large, doesn't fit in your register file, so it's going to be stored in the memory. All right, so that's how, this is what I have shown you, that here is my main memory, and let's assume these numbers are stored A0, A1 to AN-1 over there. And now I have to know a few more things. For example, I have to know exactly where is this array stored, starting where in my memory. I'm calling it the base address, so that's what is stored in location 100. I have stored a pointer. If I was to draw a pointer, then this thing is pointing to A0. This is where the numbers will be stored. And how many of them do I have? N of them, so that number is stored in location 104, and I ultimately want to sum them up, so the result will be supplied to you in location 108. Is this map of memory clear to everyone? Right? To write a general program to sum all the elements of an array, I'm going to lay out the array in the memory. I'm going to remember where the array starts in the memory. I'm going to know how many elements it has stored in 104, and then where the result will be in 108. Good. But remember, we can't compute directly on the memory, so now we have to see what happens in the registers. So in order to compute with this, I of course need all this information about base and how many elements it has and sum. So I'm going to allocate 3 registers, in my memory, and these are x1, x2, and x3, where I'm going to copy the value of the base from the memory into x1, copy the value of n from memory into register x2, and the initial value of the sum, which is, let's assume it's initialized to 0, copied from location 108 into x3. So far so good, right? And I have to right, so now let's see, this is, what will this accomplish? These 3 instructions, remember, instructions in assembly language are very, very simple. So what are these instructions doing? It's moving some information from the memory into registers, which we have agreed before we write this program how we're going to make use of these registers. So I have copied the value of base and n and sum into these three locations. Right? So these are three load instructions. Okay, and now I have to add it. So what do I do to perform this sum? What is the high level idea in performing this sum? I have something in the sum, right? And I will bring something from the memory, right? The next element to be add it to the sum, update the sum. And I keep doing this. How many times do I do this? N times, or is it n minus 1 time? I never get this right? One of those answers is correct. Okay, so after you have done all those additions, what do you do at the end? You will write the sum back into the memory, because that's where the result is supposed to be at the end. So now we have to understand how all this happens. Okay, so what is what is the first thing that is happening here? Forget about loop here. Loop is just a name for that instruction, right? So x4 gets load memory x1. x1 was the base, right? The first element of the array is in x1. So I take that. Now I have that value in x4. And what do? I add x3 and x4 and put it back in x3. Why? Because x3 is where I'm going to be accumulating the sum. So I've added x3 and x4 and put the answer back into x3. All right? Now I have done it. So now instead of summing n numbers, I have to sum n minus 1 numbers. So I decrease the value of n by 1. So this add I says, oh, one of the operands is specified in the instruction itself. Immediate, right? I'm decreasing it by 1. So minus 1 in this case. So x2 gets x2 minus 1. Are you with me so far? Okay, so now how do I know whether I'm done or not? If x2 has become 0, then you have added all the numbers, right? So there is an instruction. Let's assume there is an instruction called b not equal to 0. If z is not equal to 0, then what do we have to do? We have to repeat this whole exercise again, right? So we are jumping back to the loop. We are jumping back to the after if it is not 0, then I go back here. Why? Because I want to do this again. And I keep doing this until this becomes 0. And the moment it becomes 0, then it won't jump back. It will just fall through. It will go and do the next instruction at that point. So when you come out of this loop, what do you know for sure? You are done adding all the numbers, right? And the answer is sitting in x3. Yep.
We just forgot one instruction, which is x1 gets x1 plus 4. So point to the next element.
Sorry, x1 gets?
x1 plus 4.
Of course, otherwise it's adding the same number over and over again. Thank you. So not only do you have to decrease the n, you also have to increase I have to go from A0 to A1. What is this program doing?
That's the first element.
Sorry?
Just the first element times n.
Fantastic. It's doing something. It's just not what we wanted. Right? It's going to add A0 n times to itself. But the goal was to add A0, A1, A2, A3. So what did I forget in this? You're getting a live demo of what you do in the lab. Right? You make mistakes like this and you're convinced at that point all the tools are broken. It's almost never the case. It's always your program that is wrong, right? So get used to it, right? So you forgot that, oh my gosh, this had to be incremented by 1, and instruction is missing. So you have to insert an instruction so that next time you will go and read A1, and then you will read A2, etc. And at the end of it, you just take it and store the result into the sum. You get some idea of what's happening, right? Now this program, you have to admit, is somewhat harder to write than if you were to write this program in Python or some other high-level language. You won't have to worry about this memory and register business. You'll just write some simple loop and add up n numbers, right? Can't do that in assembly language. In assembly language, all the data movement will be in your control. If you don't specify, nothing moves, right? So by definition, this kind of programming is tedious, right? But why are we doing it if it's so tedious? Because this is suitable for building hardware, right? And in the end, we're going to have our cake and eat it too, because somebody else, another smart person, is going to translate this high-level program you have into this assembly language. That's also automated, though that's not part of this course. You'll just get a hint about that, right? So very little programming is done in assembly language. Almost all programming is done in high-level languages, and then you rely on these translators to translate it in assembly language. But for this class, you absolutely have to understand the structure of assembly language programs. And remember, we have this deep belief the only way you understand it is by doing it. So you will be writing programs in assembly language. Okay, so let's put them side by side and see, how do two things stack up against each other. If somebody says, so what is the difference between them? Well, you have, in high-level languages also, you have some primitive operations. You can say, oh, I know how to add numbers in Python because there is this plus symbol available to me, or I can compare numbers, etc. Okay, but high-level languages are not restricted to just simple operations. It can have very, very complex data types. So you can build arrays, you can build lists, you can build graphs, you can build trees, you can build all kinds of fancy data structures in a high-level language. Easy to express those things. You learn a lot of that, in various classes you take. All right? The other sophistication comes in high-level languages is that they also have a plethora of control structures which help you think about transfer of control. And there are 3 things that you remember about them. In any programming language, you need this capability of being able to execute code sequentially, right? In any programming language, you also need the ability to execute code conditionally. If something is true, do this. If something is not true, don't do this, right? This is a very essential aspect, high-level idea in conditional execution, right? That we do things under some conditions. Equally important idea is, without that programs will look very, very long, is the notion of a loop, right? That if there is some computation that is going to be done repeatedly, we could have written it as a straight line, but we'll get bored. We'll die of tedium, right? I mean, maybe this array had 100 elements, but what if it had 1,000,000 elements? I think it'll be very painful to write such a program. You write another program to generate a program, which can do that. So loops are extremely important. The moment you have some repeated computation, right, where only some parameter is changing, we always put it in a loop so that we can go over that code over and over again, right? And the last and the most powerful idea is the procedure calls. So yes, procedure calls will exist even in assembly language, but really the heart and soul of it comes from high-level languages, right? Procedure is the most important abstraction in high-level languages. You encapsulate something, you call it whatever, sort, right? And then you write another program and you just call sort. At that moment, you're not thinking what is inside sort. So there is some magic happens in the high-level language that somehow you jump there, go and sort numbers, and you come back. But while writing this program, you don't have to worry about how sort works. So high-level languages always have this. And at least when we have seen, the assembly language, I did not include any such instruction in the 4 instructions I showed you. Okay. And because of all these capabilities, because of sophisticated data structures, sophisticated control structures, this is very far removed from actual hardware implementation. If you try to implement Python directly in hardware, it will be an exercise in futility. It just won't buy you anything. You can say, oh, I should be able to write another program to do part of it, right? And I need hardware just for doing something else in it. Contrast this with assembly language, right? It also has primitive operations, and it has nothing else. It has actually very, very simple data structures. So it has primitive data structures, bits and integers. That's all we have in this. We have some weak notion of arrays, but that's primarily for addressing in the memory, and you will see that. We never talk about linked lists and this and graphs and trees when we are talking hardware. In hardware, we'll say, oh, you emulate that. You make it behave like that, and you will understand how that is done, right? Control transfer. Again, I already showed you one instruction, right? If this number is greater than that, jump somewhere. We may have variants on that theme. Instead of equal to, not equal to, less than, greater than, some conditions, some set of conditions under which you can jump, but that's it. Everything else has to be built on top of it. If you want to implement a loop, you will have to implement using that particular branch instruction, control transfer instruction. So what we will understand in the next lecture, and the lecture after that, is how this what is the connection between high-level languages and this low-level stuff we are showing. And remember, these things are designed to be directly implementable in hardware. Please remember, you do not design assembly language, you do not design machine languages so that it's easier for you to program in them. That's not an issue at all. There are only 2 issues when you design an assembly language, when you design the instruction set of a computer. One, is it suitable for implementing in hardware? And 2, do I know how to take high-level notation and translate it into this? Because you're going to have such a convoluted instruction set that no sane person can write a translator for you. Right? So it's a target of some high-level language, right? But the thing you do not worry about is it convenient to write programs in assembly language? Because you're not expected to write programs in assembly language. And the thing you will discover very rapidly is, say, man, this is tedious, right? So if nothing else, it will make you believe in high-level languages even more, right? But in this class, you cannot learn about how computers function unless you understand assembly language. Okay, so let me briefly give you the course outlined. And I have just sort of organized it in few modules so that you can remember. So module number 1 is, we want to understand how numbers are represented in the binary form, how do we carry on operations in them. Then we will introduce this RISC-V instruction set architecture. The specific instructions we'll be using is an ISA called RISC-V, and this is cool. I mean, this is the first one which is under no legal hassles. It's open source. You can implement it any which way you want. If you implemented x86, you will get a summon from Intel. You're violating their copyrights and they'll put you in jail, or at least they'll demand a lot of money from you, for doing that. So there is no such hassle with RISC-V. It's great. And you'll be doing assembly language programming, expressing high-level language constructs into assembly languages, and procedure calling convention, which will take some effort to understand, right? There's a very specific procedure calling convention that is used. Module 2, now we will change, right? So anything I want to teach you about programming, we are done with, right? So because assembly language is all I need in order to build computers. Now we will get into hardware design. And hardware design is, what? Combinational logic and sequential logic, and how do you put these things together so that you can keep building more and more complex circuits. And there is a lot to be learned over there, because as I said early on, microprocessors are some of the most complex things known to human beings, right? Designed by human beings. So there's a lot to learn. And here again, just as we are using something very new called RISC-V, here we'll be using BlueSpec, right? So the difference is most hardware languages tend to be very low level, and they're really annoying, right? I mean, they say, man, this is archaic stuff, right? Not in BlueSpec. So BlueSpec is really informed by modern ideas in programming, and more software easier you will find how to use BlueSpec. But at the same time, you cannot write BlueSpec programs unless you have a hardware model in your head. Because the goal of BlueSpec programs is not to generate answers, it's to generate circuits, right? You write something and it'll produce circuits for you, right? So we'll face it when the time comes. Then we will go to module 3, where now this RISC-V stuff that you have learned in the beginning, we will plunge into it. We will get into implementing that stuff. We will show you how we can actually build computers that execute any program you can write in RISC-V assembly. And by extension, any program you can write in Python which can be translated into RISC-V assembly. Okay. And there is no end to it. I mean, we can just keep going. So somewhere we have to say, okay, we have no time left. We'll just stop at this because these machines can get arbitrarily sophisticated. Then we'll switch gears, and you will discover that modern systems cannot function. It's not that you have a naked machine and you run programs on it. The way systems work these days is you have a naked machine, and then we have to put some software on it before it becomes usable. And that software is very important. You have to understand the basics of it, and that's called operating system. And to understand that level of operating system detail, you have to understand both something about software as well as something about hardware in this. So that's why this is an important topic in this class. And then finally, we will see what extra headaches arise when we have multi-cores, when we want to do parallel programming, etc. So depending on how much time we have, we can go into as much detail as time permits over there. Now, I briefly mentioned that we'll be using BlueSpec. This is very important in this class, right? We rely on modern design tools, and by that we mean BlueSpec or BSV, BlueSpec System Verilog. And the way to think about this is, you write your code in BlueSpec, and there is a compiler that translates it into circuits which you can simulate, right? So there is a simulator on this side. But the same code, if you want, you can put it through a different translators, and it will produce actual gates that can be synthesized. You can run them on FPGAs. You can actually go and and issue a design to a factory. Make me this chip, etc. We won't have enough time to do this latter part, but whatever you're writing here is automated. You can go down to the actual hardware anytime you want, from it. So designs are always expressed in high-level programming language, which is compiled to generate circuit descriptions. In other words, even though we are talking of billions of gates, you'll never be thinking like that. Those gates are always going to be generated from some high-level description in automated way, and it's a very important part of this class to understand how does that happen. What is the correspondence between the codes you write and the gates that will come out of it. And this is the finale. This is the best part of this course. So in the end, there's a project, right, where you will design RISC-V processors, and part of it is open competition. Let's see who can do better, right? This is just to show you that one of the teaching assistants last term designed all these processors in less than 2 weeks. These are all different RISC-V processors. They're all capable of executing the same programs, and they have different capability. Some are faster, some are smaller, and so on. So this is where you will get. I mean, if you understand it, you know how to do this, you say, oh, I wonder if I can beat the TA, if I can beat, you know, it's very easy to beat me, so I won't put myself up in the competition, right? But really, you'll have great fun designing, and this is all part of the project in this. So course mechanics, I'm going to hand it over to Silvina, and she'll quickly explain you the course mechanics.
I'll go over this in more detail next time, but just at a high level, I just want to point you out to our website, which is at 6004.mit.edu. You should all go there today and take a look at it. We rely very heavily on Piazza, so you should go ahead and sign up for the 6004 Piazza today. We do course announcements and all sort of things there, and already I put up a poll asking about course handouts. We'd like to not print out these handouts and instead just have it all online, so please respond to that poll sometime this week. Very high level, you know, we have 2 lectures per week. We have also 2 recitations per week. It doesn't really matter which recitation you're assigned to, just go to the one that works for you, and we'll just make sure that they're balanced in terms of how many people are in each, so that it's a good learning experience. You're going to have 8 mandatory lab exercises in this class. In order to pass the class, you must pass all 8 labs. You cannot, you know, not pass one of them, otherwise you will fail the class. However, there will be lots of help in order to help you pass each of those labs. We also give you some free late days. You have 7 free late days to use however you want during the semester, but please make sure to realize that we want you to use those, you know, if you have a small illness or things like that, don't come asking for extra late days. That's what those late days are for. And then at the end of the term, there will be an open-ended design project, and we have 3 quizzes where the dates are already specified. Just a couple other things. We've canceled 2 of the recitations based on registration for this course. So if you were registered for recitation 11 or 12, don't go to it because it doesn't exist. Recitations are mandatory in this class. We think it's really important to, there's certain material that we're actually going to opt to teach in recitations rather than lecture. So number 1, you might see new material in recitations, and number 2, the types of problems we go over in recitation are really critical in order for you to be able to do the quizzes in this class. And for recitations as well, we give everybody 4 excused absences. I'll skip this part for now. And finally, grading. So each of the labs is going to be worth 10 points for a total of 80. The design project is worth 20 points. Sorry. The quizzes are 30 points each, and 10 points come from recitation for a total of 200. And just to give you a sense for last year's cutoffs, I've listed them here. They're not going to necessarily be identical to last semester, but it gives you a sense for where you need to be in order to get the grade you might be looking for. And just so you know, our lab is in 32083. There's a combination for it in case nobody is there. It's a very secret combination, so we don't write it, but I'll tell it to you. It's 7755331. Remember that. It hasn't changed in very, very many years, so lots of your fellow MIT students know it. And the last thing is we're going to do a bunch of surveys throughout the semester in order to try to improve upon this course, since, as you probably know, this is a new way of teaching the class, and we really, really care about your feedback, so make sure to participate in those. Okay, any questions? Ask them on Piazza. We are very good about answering them. Thanks.